Welcome to the deep dive. We take complex subjects, break them down, and give you the key insights you need, fast.
That's the idea.
So today, I want you to just, look up. Think about the night sky. All those stars, the darkness. Doesn't it make you wonder?
It absolutely does. Those big questions like, where did it all come from?
Exactly. And that sense of wonder, those huge questions, that's what drives our deep dive today into, well, the cosmos and cosmology.
Right. We're going beyond just thinking about it into the actual science, the quest to really understand everything that exists.
Yeah, that's our mission here. We've pulled together some really fascinating material to sort of unpack the universe's origin, its structure, how it's changed over time, and, well, where it's all heading.
Think of it as your shortcut to getting your head around these, frankly, mind-bending ideas.
I'm really excited to get into this. Some of the concepts are just, wow.
And I'll be here to help guide us through the sometimes tricky ideas, connect the dots, and sort of show why this stuff really matters, why it changes how we see everything.
Okay, so to kick things off properly, let's get our terms straight. What exactly is the cosmos? And how is that different from cosmology? They sound similar.
Good starting point. So cosmos comes from the Greek cosmos. It means things like order, universe, world.
Okay.
And basically, in the biggest sense, the cosmos is everything, literally everything. All of space, all of time, all matter, energy, and the physical laws that run the whole show.
Wow. So everything means everything, like from the tiniest particle you can imagine, smaller than atoms, all the way out to the most distant galaxies we can see.
Exactly, from the very start of time to whatever the end might be. Yeah, all-encompassing.
Yeah.
And then you have cosmology. That's the science of the cosmos. It's the study of where it came from, what its structure is, how it evolves, and, its ultimate fate.
Ah, okay, so cosmology is the study of the cosmos.
Precisely. It's a branch of science, mainly astronomy and physics, but it pulls in lots of different fields.
So it's not just astronomers looking through telescopes.
No, not at all. You've got astrophysics, obviously, studying stars and galaxies and things, but also particle physics, looking at the fundamental building blocks.
Right.
And then you need Einstein's relativity to understand gravity and space-time, plus quantum mechanics for the really small scales in the early universe. It's a real mix.
Okay, let's unpack this, the origin story. When we talk about how the universe began, the Big Bang Theory is the one everyone's heard of.
It is. It's the most accepted scientific model we have.
But that name, Big Bang, it sounds like a huge explosion in space.
Right.
I gather that's not quite accurate.
That's a really common misconception, actually. It wasn't an explosion into empty space. The theory says the universe started about 13.8 billion years ago.
A few 0.8 billion, okay.
From this incredibly hot, incredibly dense state, sometimes called a singularity. And from that point, space itself began expanding rapidly.
Ah, the expansion of space, not into space.
Exactly. And it's still expanding today. That's crucial.
So what convinced scientists this was the right track? What was the key evidence, the sort of aha moments?
Well, there are several big ones. One of the absolute pillars is the cosmic microwave background, the CMB.
Right, the CMB. That's like leftover heat.
Sort of, yeah. It's this faint microwave radiation bathing the entire universe pretty much uniformly. It's like a residual heat, an echo from that very hot early phase, a relic of the Big Bang itself.
An echo from the start of time. That's amazing. Okay, what else?
Then there's the redshift of galaxies. You know how an ambulance siren sounds higher pitched coming towards you and lower going away?
You have the Doppler effect.
Exactly. Light does something similar. When galaxies are moving away from us, the light waves they emit get stretched out, shifting towards the red end of the spectrum. We call that redshift.
And we see that galaxies are redshifted.
Overwhelmingly, yes. And crucially, the farther away a galaxy is, the more redshifted it is, meaning it's moving away faster. This tells us space itself is stretching, carrying these galaxies away from us.
Which brings us to Hubble, Edwin Hubble. He figured this out, didn't he?
He did. His observations in the 1920s showed this relationship. Farther equals faster. This led to Hubble's law.
Right, the equation. V equals h0 times d.
That's the one. Velocity equals the Hubble constant times distance. It's simple, but profound. By measuring velocities and distances, we can calculate that constant, h0.
And that tells us the expansion rate.
And from the expansion rate, you can work backwards to figure out the age of the universe. That's how we get the 13.8 billion year number. It all connects.
That's incredible. Okay. So CMB, redshift. Was there a third piece?
Yes. the abundance of light elements,
Hmm.
specifically hydrogen and helium.
Okay.
The Big Bang model predicts exactly how much hydrogen and helium should have been formed in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion, but before any stars existed.
And the amounts we see out there match the predictions.
They match remarkably well. It's strong evidence that the early universe really was like the model describes.
Wow. Okay. So the universe started hot and dense. It expanded. It's still expanding. But what did that expansion create? What does the universe actually look like on the grandest scale? It's not just evenly spread out stuff, is it?
No, definitely not. There's a very clear structure and architecture to the cosmos. It's hierarchical,
Mm.
meaning stars group together into galaxies, galaxies then clump together into clusters, and even those clusters form larger groups called superclusters.
So clusters of clusters.
Pretty much. But it's not just clumps. There are also these huge regions that are relatively empty with very few galaxies. We call them cosmic voids.
Right, the voids. So
Yeah.
it's like a network.
Exactly. That's the term cosmologists use, the cosmic web.
Hmm.
Imagine immense filaments of galaxies and clusters stretching across billions of light years surrounding these vast empty voids.
Yeah.
It's this interconnected structure that defines the large-scale universe.
Okay, a cosmic web. But then comes the really weird part. All that stuff we can see, the stars, the galaxies, us, that's only a tiny fraction of what's actually out there, isn't it?
That's probably one of the most startling discoveries in modern cosmology. All the normal matter, the atoms that make up everything we know and interact with, that's only about 5% of the total energy and matter content of the universe.
Only 5%. So what's the other 95%?
Well, about 27% is something called dark matter, and the remaining 68% is even more mysterious. Dark energy.
Okay, dark matter first. It's dark because we can't see it, doesn't give off light.
Correct. It doesn't emit, absorb, or reflect light or any electromagnetic radiation we can detect. So totally invisible to our telescopes.
How do we know it's even there?
Through its gravity. We see its gravitational effects on the stuff we can see. For example, galaxies rotate much faster than they should, based on the amount of visible matter they contain.
So something invisible must be providing extra gravity to hold them together.
Exactly. There has to be this massive halo of invisible matter surrounding galaxies, providing the extra gravitational pull. We see its effects also in how light bends around galaxy clusters' gravitational lensing. That shows much more mass than we can see.
Okay, so dark matter provides extra gravity. What about dark energy? That's the biggest chunk, 68%. Here's where it gets really interesting.
It really does. Dark energy is, well, it's even stranger. It seems to be some kind of energy inherent in space itself, and it has the opposite effect of gravity. Instead of pulling things together, it's pushing things apart.
Pushing space apart, so it's driving the expansion.
Not just driving it, but causing the expansion to accelerate, to speed up over time. This was discovered in the late 1990s by observing distant supernovae, and it was a huge shock. We expected gravity might be slowing the expansion down, but instead, it's accelerating.
Wow. So most of the universe is made of stuff we can't see and don't really understand, and one part of it is making the universe expand faster and faster.
That's the current picture, yes. And the implications are profound. It means our fundamental understanding of physics might be incomplete. We don't know what dark matter particles are. We have ideas, but no proof yet. And dark energy, its nature is one of the biggest mysteries in all of science. Does it change over time? Is it related to the vacuum energy predicted by quantum physics? We just don't know.
It's humbling, really, to realize how much is still unknown.
Absolutely. It tells us there's so much more to discover, perhaps entirely new physics.
Let's circle back to something we can detect, even if faintly. The cosmic microwave background, the CMB. We said it's evidence for the Big Bang, but you mentioned it's more than that.
Oh, much more. Its discovery itself is a great story. Arno Penzias and Robert Wilson in 1965. They were engineers at Bell Labs working on microwave receivers for satellite communication.
Right.
And they kept picking up this persistent background noise, this hiss, no matter where they pointed their antenna. They checked everything, even cleaned out pigeon droppings, thinking it was interference.
Pigeon droppings causing cosmic static.
Huh. Well, they ruled that out. Eventually, they realized, after talking to physicists at Princeton who were actually looking for this exact signal, that they had accidentally detected the leftover heat from the Big Bang. They won the Nobel Prize for it.
An amazing accidental discovery. So this light, this oldest light, you said it dates from about 380,000 years after the Big Bang. What was special about that time?
That was a critical moment called recombination. Before that, the universe was so hot that electrons and protons were just flying around freely in a dense, opaque plasma. Light couldn't travel far without bumping into charged particles.
Okay, like a thick fog.
Exactly. But around 380,000 years, the universe cooled down enough for electrons to combine with atomic nuclei, mostly hydrogen and helium, to form the first stable neutral atoms. Suddenly, the fog lifted.
And the light could travel freely.
Yes. The light that was present at that moment could finally stream across the universe unimpeded. And that's the light we see today as the CMB. It's been traveling for over 13 billion years, stretching out into microwaves as the universe expanded.
So it's literally a snapshot of the moment the universe became transparent.
Precisely. It's like the universe's baby picture. And it's not perfectly uniform. There are tiny temperature fluctuations, like ripples, across the CMB sky.
Ripples, what do they mean?
Those tiny variations, just fractions of a degree, represent slightly denser and less dense regions in the early universe. Those denser spots were the seeds, gravitationally attracting more matter over billions of years, eventually growing into the galaxies and clusters we see today. The CMB map is essentially the blueprint for the cosmic web.
Wow. So much information packed into that faint glow. Okay, let's try and trace that whole journey. Can you give us a quick rundown of the cosmic timeline, the major beats from the Big Bang to now?
Sure. So time zero, the Big Bang itself, then almost instantly, like 10 to the minus 34 seconds.
Unimaginably fast.
An era called inflation is thought to have occurred. Super rapid, exponential expansion blew the universe up incredibly quickly.
Inflation. Okay, then what?
By about a millionth of a second, 10 or less, things had cooled enough for quarks and gluons, fundamental particles, to form.
Right.
Then, around 1 second after the Big Bang, protons and neutrons formed from those quarks. Just 3 minutes in, the first atomic nuclei, hydrogen and helium, mostly were forged in what's called Big Bang nucleosynthesis.
So the ingredients for the first atoms were ready very early on.
Yes, the nuclei were. But it took until about 380,000 years for things to cool enough for electrons to join them, forming those neutral atoms and releasing the CMB light. That's a major milestone.
The universe becomes transparent.
Exactly. After that, gravity started doing its work on those tiny density fluctuations seen in the CMB. Slowly, over hundreds of millions of years, matter started clumping together. Around, say, maybe a few 100 million to a billion years after the Big Bang, the first stars ignited and the first galaxies began to form.
And from then on, it's been galaxies forming, merging, stars living and dying.
Leading up to today, 13.8 billion years later, with the complex structures, the cosmic web, dark matter, dark energy, and us here trying to figure it all out.
It's quite a story. All that action crammed into the first moments and then billions of years of evolution. Now, something else fundamental is the shape of the universe, the geometry of space itself. It's not just flat, empty space.
Well, it might be flat, but it's not a given. Einstein's general relativity tells us that mass and energy curve space-time, so the overall distribution of mass and energy in the universe determines its geometry.
And there are different possibilities for that overall shape.
Yes. Traditionally, cosmologists talk about 3 basic possibilities based on the curvature of space. Imagine them like 2D surfaces to make it easier.
Okay.
It could be flat, like a sheet of paper. This corresponds to 0 curvature. If it's flat and infinite, it would expand forever, but the expansion rate would approach 0 over infinite time.
Flat. Got it. What else?
It could be open, which has negative curvature, like the surface of a saddle. Harder to picture, but mathematically distinct. An open universe would also expand forever, and possibly accelerate depending on dark energy.
Okay. Saddle-shaped.
And the third possibility is closed, with positive curvature, like the surface of a sphere. A closed universe is finite in volume, though it has no edge, and contains enough mass and energy for gravity eventually to halt the expansion and cause it to collapse back in on itself.
The big crunch scenario.
Exactly. So flat, open, or closed. Those are the possibilities determined by the total density of matter and energy compared to a critical value.
And where does the evidence point now?
Yeah.
What shape do we think our universe is?
The best evidence we have, especially from detailed measurements of the CMB fluctuations and observations of large-scale structure, strongly indicates that our universe is very, very close to being flat.
Flat. So likely expanding forever, maybe slowing down slightly, but then there's dark energy accelerating it. It gets complicated.
It does. The flatness is actually one of the things that inflation theory helps explain.
Okay, let's connect this to the bigger picture, like you said. These advanced ideas. Inflation theory, why is it so important? You mentioned it happened right at the start.
Right. Inflation proposes this period of incredibly rapid exponential expansion, just fractions of a second after the Big Bang. It sounds wild, but it elegantly solves some major problems with the standard Big Bang model without it.
Like what problems?
One is the horizon problem. The CMB looks incredibly uniform in temperature across the entire sky. But in the standard model, without inflation, regions on opposite sides of the sky wouldn't have had time to interact or exchange heat to reach the same temperature. How did they coordinate?
Ah, okay. How do they know to be the same temperature if they couldn't communicate?
Exactly. Inflation solves this by saying the entire observable universe we see today started from a tiny, causally connected patch that was then stretched exponentially. So everything was in contact early on.
Clever. And the flatness problem.
Yes, that's the other big one. Why is the universe so close to perfectly flat? Any tiny deviation from flatness in the early universe would have been massively amplified over billions of years. For it to be this flat today requires incredibly fine-tuned initial conditions, which seems unlikely.
But inflation helps here too.
It does. The rapid stretching during inflation would have naturally flattened out any initial curvature, like blowing up a wrinkled balloon until the surface looks flat locally. So inflation makes flatness a natural outcome, not a coincidence.
Okay, that makes sense. Now, what about the multiverse? That's an idea that really captures the imagination. Our universe isn't the only one.
Well, that's the hypothesis. It's definitely more speculative than inflation, but it arises from certain physical theories, including some models of inflation and interpretations of string theory and quantum mechanics.
So what's the basic idea?
The idea is that our universe might just be one bubble or region within a much larger, perhaps infinite multiverse. Inflation might not stop everywhere at once. It could continue in other regions, constantly spawning new universes.
Wow. And these other universes, could they be different?
Potentially, yes. They might have different physical laws, different fundamental constants, maybe even different dimensions. It's a way some physicists think about why our own universe seems so finely tuned for life. Maybe there are countless others where the laws aren't right and we just happen to be in one that works. But it's very hard, maybe impossible, to test experimentally right now.
Mind-bending stuff.
Oh.
Okay, finally, the ultimate question cosmology tackles, the fate of our universe. You mentioned the Big Crunch, but with dark energy accelerating things, that seems less likely now.
That's right. Given the dominance of dark energy that we currently observe, the Big Crunch seems unlikely unless dark energy behaves very differently in the future.
So what's the front-runner prediction?
The most likely scenario, based on current data, is often called the Big Freeze or the heat death.
Sounds chilly.
It is. At this scenario, the universe just keeps expanding faster and faster. Galaxies get further and further apart. Star formation eventually ceases as all the gas is used up. Existing stars burn out. Black holes might eventually evaporate over trillions and trillions of years through Hawking radiation. The universe just gets colder, darker, emptier. Entropy wins.
A rather bleak ending. Are there any other possibilities?
Well, there's the big rip. This depends on the exact nature of dark energy. If dark energy grows stronger over time, something called phantom dark energy, the accelerating expansion could become so powerful it overcomes gravity, then the electromagnetic force, then the strong nuclear force.
Tearing things apart.
Yes. First, it would rip apart galaxy clusters, then galaxies themselves, then solar systems, planets, eventually even atoms and nuclei. Everything gets torn asunder. It's a dramatic end, but maybe less likely than the Big Freeze based on current measurements.
Freeze, crunch, or rip. Quite the cosmic choices.
Yeah.
So how do scientists actually study all this? The origins, the fate, dark matter, what tools do they use?
It's a whole arsenal, really. Telescopes are fundamental, of course. Optical telescopes like Hubble and now James Webb let us see distant galaxies peering back in time. Radio telescopes map things like hydrogen gas and the CMB. X-ray and gamma-ray telescopes probe high-energy events.
So observing across the spectrum.
Absolutely. But it's not just looking. Computer simulations are incredibly important. We can't run experiments on the whole universe, but we can create model universes inside supercomputers.
Test theories.
Exactly. We can simulate how structure forms over billions of years with different amounts of dark matter and dark energy and see which models match observations. We simulate galaxy collisions, star formation. It's crucial for interpreting what we see.
And what about recreating the very early universe?
That's where particle colliders come in, like the Large Hadron Collider at CERN. By smashing particles together at incredibly high energies, they recreate conditions similar to those just fractions of a second after the Big Bang. This lets physicists test theories about fundamental particles and forces that govern that early era.
Telescopes, simulations, colliders. A powerful combination. Okay, one last clarification. We've used terms like cosmology, astronomy, astrophysics. Can you quickly distinguish them again? Sometimes they seem used interchangeably.
They are related but distinct. Think of it this way. Cosmology is the big picture, the study of the universe as a whole entity, its origin, evolution, large-scale structure, and ultimate fate.
The whole story.
Right. Astronomy is more focused on the observation of celestial objects, stars, planets, galaxies, nebulae, measuring their positions, brightness, motions, classifying them. It's the what's out there.
Cataloging the universe.
Sort of, yes. And astrophysics is about applying the laws of physics to understand how those objects work. What physical processes make stars shine? How do galaxies form and evolve? What happens inside a supernova? It's the physics behind the astronomy.
Okay. Cosmology, the whole story. Astronomy, the characters and settings. Astrophysics, the laws governing their actions.
That's a pretty good analogy, actually, yeah.
Perfect. This has been, well, cosmic, a truly fascinating dive. It really brings us back to that initial feeling of awe when you look at the sky.
It does. It tackles those fundamental human questions. Where did we come from? Why is the universe like this? Where is it all going?
And it really showcases, human curiosity, our drive to understand even things that seem almost incomprehensible.
Pushing the boundaries of knowledge, definitely.
So, for everyone listening, maybe take a moment to think about your own place in all this vastness. Does knowing about dark matter, dark energy, the Big Bang, does it change how you see things?
And maybe ponder this. Considering that 95% of the universe, dark matter and dark energy, is still largely a mystery, what completely new physics, what unexpected discoveries might be just around the corner, discoveries that could fundamentally rewrite everything we've talked about today.
A great thought to leave us with. Thank you so much for guiding us through this.
My pleasure. It's fascinating.